So normally when you use GDB, it's because you've got a bug in your program and you want to find out where that bug is. So what I'm going to do is I'm going to add a bug to my program, and what I'm going to do is I'm just going to comment out this call to melon. So this should mean that entries points to some random location in memory, whatever it happened to be before, and when we start trying to write to entries down here, this should actually crash the program. Now, it's not 100% guaranteed that it will crash because that could just through sheer luck happen to point to a valid memory location, but hopefully this will actually crash. So I'm just going to recompile that and then run it. Okay, so we've got a segmentation fault. I'm sure you've probably seen this happen before, more than once. So with GDB, we can actually track down where is this segmentation fault, why is this happening. So I'm going to run GDB from Emacs again. Now this time I'm not actually going to set a break because what I want GDB to do is to break as soon as the program has a segmentation fault. So I'll just type run and give it the command line parameters. Okay, so we'll see that it has received this error, kern invalid address at address all zeros. So this means I've tried to dereference a null pointer. Now if we look at the place that calls get sorted entries, we will see that this is passing a reference to a local variable which has not been initialized. Now in this particular case, that has the value 0, right? It's null. That's not necessarily going to be the case in all situations, but it's just through sheer luck that happens to have been null in this case, and we've got the segmentation. So this is showing us that it's happening on compare.c line 39. Okay, and you'll see again that that's got a little arrow next to it showing where we are. And I think on Linux that will highlight the whole line. So the mistake in our program is here, but where we're getting the error is actually here. So this is reporting the error the first time we try and write to that bad memory. So what I can also do in GDB is I can type backtrace. So if I want to see what functions have been called to get here, I type backtrace and enter, and that will show me what functions have been called. So the first one was main, and then main called compare, compare called compare DIRs, and compare called get sorted entries. BT, by the way, is a abbreviation for backtrace. So you can type BT to go to. Now, I can look around my code here, but maybe the problem is further up. So supposing I want to go to the function that called the current one. So we're currently at frame number 0, which is at the top of the stack. If I type frame 1, that will take me to the function call that was directly above that. And it will show me where in that function call it was. So it was get sorted entries. If I type frame 2, or similarly I can just type F2 as an abbreviation, that will go to frame 2. So that will go to the function call above that. So I can actually jump through my stack and see where it was at each point. The highest level was main, and main was inside the call compare. In frame 2, that was inside the call to compare DIRs. And within compare DIRs, that was calling the get sorted entries function, and then get sorted entry was at this particular one. And I could also print out start just to see what that is, and I would see that is 0. Okay? So what the program is doing in this particular case is it's attempting to dereference a null pointer. The way that I would debug that is I would look at what is the variable that it's trying to dereference, and then I would trace back and see where that variable is initialized. And in this case, I haven't initialized it because I've commented out that code. So to fix that, I would uncomment that line of code, save the file, recompile it, and then if I wanted to run it through GDB again, I would need to quit GDB and then load it again. Sorry, that's supposed to be path 1 and path 2. And we'll see that in this case it completes successfully. Okay, so GDB is very handy when you get segmentation faults because you can see exactly where in your code the seg fault has occurred. And when it's occurred, you can look at the values of variables in your program at the time that the crash occurred. So just remember, when you compile, you have to pass the -G flag to GCC. That includes the necessary debugging information. And you should be doing this anyway, all the time. The -wall flag brings up any warnings about potential mistakes you've made. Okay, so now I'm going to show you another program that you can use for debugging. GDB won't necessarily catch all of the errors. You may be doing things that are errors, but as it happens, they don't show up. So for example, in C, it's possible to free memory and then write to it after you've freed. Now, it's incorrect to do that, but if you do that, sometimes it will actually work, and sometimes it won't. So what I'm going to do is I'm going to add another line of code here where I say free star entries. And what it will do is it will mark that memory as unused, but if I try to write to it here, then depending on sheer luck, this may or may not work. The last time I gave this demo, it actually successfully executed that line, and then it ended up crashing at some later point. So I'm going to try this and see what happens. Okay, so in this case I'm still getting a crash, but this is a crash that is occurring later, and I'll show you how I know that. So what I'm going to do is I'm going to run through GDB again. So Control X2 to split this in two. File compare. Run with path 1 and path 2. And we will see that this has gotten an error. Now, the way that this particular error is occurring is that the malloc routines in Mac OS X will actually check the consistencies of their data structures. And sometimes if you've overwritten it, then it will pick that up as an error. And in this case, it's actually executed. So what this is, and I think this works a bit differently under Linux, but what this has told us to do is set a breakpoint in malloc error break to debug. So we already know how to do that, right? We say B for break, and then malloc error break. Okay, so we set a breakpoint inside the C library, and the program will get to that point if we do an invalid memory access. So we'll run this again. Okay, and that hasn't actually picked it up, but I would expect that it would. Let me just try this outside of Emacs. Right, okay, so this has still stopped it. It's just stopped it later than when the error occurred. But at any rate, it's actually stopped the program, and the error is occurring in free strings, which is called from compare dir. So we go to compare.c line 54, and the error, it's not line 54, that's line 64, we want line 54. So the error is occurring here, which is, and free strings is called from here. So we've done some invalid memory accesses, but we're not picking up that that's a problem until much later on in our execution. So during the time at which we've freed the memory here, we're writing to the freed memory, and we're doing all this other stuff. We're actually in a very dangerous state because we're accessing memory and specifically writing to memory that has been marked as free, and that is going to cause memory corruption, which may not turn up until later in the program. So these sorts of errors are really nasty to debug. So there's another tool which I'm going to show you called Valgrind, which actually does a much better job of detecting these problems. Now, there is a version of Valgrind for OS X, but it's not very mature. So what I'm going to do is I'm going to log into a Linux machine and run it on that because it works a lot better on Linux. So I'm just going to do that now. And this is actually a Linux virtual machine that I'm running under VMware on my laptop. So I'm going to change into the directory where my files are. Okay, so I need to recompile the program under Linux, of course. Okay, so I've now produced an executable for Linux. We'll just run this under Linux and see if we get the same crash. So this is, don't worry about that, that's a normal error. We've got the segmentation fault here, okay? So let's run this under GDB under Linux first. Okay, it's received a segmentation fault, and this has occurred in the strconf function. We'll do a backtrace on that, and in this particular case it's occurred in the qsort function, which we've called from compare strings. Now, the reason why this has occurred in a different location is, well, part of it is luck, and part of it is the fact that the way in which the memory allocators work under Linux and OS X is different. But either way, when you're doing something dangerous like writing to memory that you've freed, it's pretty much game over already because the program could potentially run into an error at any point. Because when we're writing over this freed memory, some other part of the program could allocate memory and think it's got exclusive access to that region of the address space by itself, but in actual fact be looking at something that you've written to from somewhere else, and that's where the corruption can come from. Okay, so we want to trace down where is this problem happening, and for that we can use Valgrind. Valgrind is your best friend when you're doing C programming. It makes your life much easier. What Valgrind does is it runs your program through an emulated x86 CPU, and it tracks every single read and write